Hello, astronomers. Newland here. Let's talk about luminosity and how it plays into information that we'd like to gather about stars. So I have one of the slides from our notes here. You can see that here's the slide that I was using to talk about the uh, black body curve, and there's Wien's law, lambda max equals B, which is a constant over T. So what is luminosity? Luminosity is literally all of the energy leaving the whole star. So it's got two different parts. It's got one term, 4 pi r squared. That is the surface area of the star. The bigger the star is, the more the 4 pi r squared has an impact on the luminosity. But the other part of luminosity is sigma t to the fourth. Sigma is a constant. T to the fourth is obviously a much bigger sort of impact. So the temperature is a very important thing, but I wanted to talk about the stellar radius as well, because we consider in astronomy a dwarf star to have about the sun's radius or smaller. That's considered a dwarf, so the sun falls into that category, obviously. But giant stars are between 10 and 100 times the radius of the sun, and things bigger than that are called supergiants. And so one factor in the luminosity is the 4 pi r squared. So you can have two stars that are the same temperature, but they have different radii. The bigger star is going to be brighter. Luminosity is a function of r squared. So do know, though, that if the temperature changes a little bit, that two different temperatures are going to have a bigger impact on luminosity than two different radii. So, all right, I've got here a lab I used to use. It's kind of become hard to use because it uses flash, but it's got a little calculator built into it. So here's the O, be a fine, gorilla, karate me. O stars and B stars are blue. So some of the A stars are also blue, but F and G, and you can say F kind of falls into the almost getting to be yellow. Then there's F and G, which are the yellow ones. And then there's K's and M's, which are orange and red. So this little slider lets me change the temperature, which is also the color because of Wien's law. And notice if I get a G2, that's the same as the sun. And here I can change the size of the star. And if I want it to be the same radius as the sun, I make this 1, not 1.1. And so you can, with this gadget, change either the 4 pi r squared or the sigma t to the fourth. So notice that when you change the sigma t to the fourth by changing the temperature slider to the different spectral types, very blue, starting to become yellow, starting to become orange, finally becoming red. So O, be a fine, gorilla, karate me. 30,000 Kelvin on this end, about 6,000 Kelvin here, and 2,000 Kelvin way down there. So what's going on? Actually, it looks like 2,300. What's going on is that either of these two things can physically affect the star, which physically affects the luminosity. So if you've got a big star and it's blue, then it's way more bright than the sun. But if that same big star, the temperature goes down, it's still brighter than the sun, but now it's 300 as opposed to that was times 10 to the seventh. So 7 times 10 to the seventh. So that would be 78 million times brighter than the sun, and here it's only 246. So temperature has a bigger impact on luminosity than the radius, but they both have an impact. Luminosity, by the way, if I plotted it, let's switch to this other gadget here. If I plot luminosity on the y-axis, and I plot the temperature on the x-axis, I end up with something known as the Hertzsprung Russell diagram. So this little interactive tool shows several things all at the same time. The y-axis is luminosity, which is also the brightness of the star. It's also the absolute magnitude of the star. So notice in the y scale, I can make it magnitude, absolute magnitude, or luminosity. They mean the same thing. And then on the x-axis, I can make it temperature, with the hotter actually being closer to the left-hand side, the cooler being farther to the right, or I can make it the spectral type. OB affine gorilla karate me. And because of Annie Jump Cannon's original Harvard scale, the Hertzsprung Russell diagram was actually laid out with the Annie Cannon scale along the x-axis, which means the temperature is actually on the left if you do that. The redder it is, the farther along the x-axis you go. The bluer it is, the closer to the origin you go. But that means the temperature is hotter on the left and cooler on the right. So if we have increasing wavelength across the bottom axis, which makes perfect sense, you end up accidentally, because lambda and t are inversely proportional, wavelength and temperature are inversely proportional. Lambda times t is a constant. As the thing gets redder, it gets cooler. As it gets bluer, it gets hotter. So this is known as the Hertzsprung Russell diagram, and it is definitely dependent on the luminosity. So notice if I plot and then if we also wanted to include the 4 pi r squared, these green lines are known as isoradial lines. So you can incorporate them onto there as well. Oh, by the way, you can drag the little sample star around and it compares the size to the sun. So you can see it doing that. So these would be 1,000 times the radius of the sun. Here, every star on this green line is the same radius as the sun. Every star there is a hundredth the radius of the sun, that kind of thing. So it's actually got the t to the fourth piece along the x-axis, but it has at this sort of like diagonal here, it also has the radius on there as well. So if we plotted the nearest stars to the sun, we'll see most of them are pretty darn red, and that would also make them cooler than the sun. They all line up along this thing here called the main sequence. And then let's do the brightest stars. You'll notice that the brightest stars are pretty darn blue, except some of them fall into this kind of cloud zone over here. Hey, let me um, turn on a little feature here. The red sort of cloud that they've drawn there, these are stars that are known as red giant stars. The green kind of thing in the middle is known as the main sequence, which is where the dwarf stars are located. Then there's the this little zone down here called the white dwarf zone. So these guys count as giants. That was 10 to 100 times the radius of the sun. But the ones up here are supergiants. They are bigger than 100 solar radius, more or less. Notice it's a cloud, so it's not like it's 1 to 1. So the main sequence turns out to be the grouping of stars that you would find if those stars are fusing hydrogen into helium. So that's what's going on. The ones in the red cloud up here, they're not doing that. They're doing something else. And the ones down here in this sort of gray zone, here I'll turn on the nearest stars. You can see, well, none showed up. So let's turn on we'll turn on everything at once. So you can see the main sequence very clearly. There's still nothing in the white dwarf category. There's some red giants here in this sort of zone, and there's some really big, rare stars called supergiants that are way up here. Some of them are blue, some are red. There's even some yellow supergiants. So that's kind of a weird, rare category. So notice the Hertzsprung Russell diagram, increasing brightness or luminosity on the x-axis, or if we do magnitude, that would make the negative numbers higher up and positive numbers, which are dimmer, farther down. And then along the x-axis, we can put the spectral type, the OB affine gorilla karate me, or we can put temperature, because they mean the same thing. And there's even a third category called B minus V, or the color index. If we take the magnitude of a star with a blue filter, and then we take the exact same magnitude of that star with a green filter, which is known as visual, and we subtract the two, the more negative it is, that means it had more blue light. The more positive it is, that means it had more red light. Remember, magnitude is backwards. A negative number means brighter. So a more negative number means that B minus V must have had more blue in it. A more positive number means that B minus V must have had more red in it. So that's actually a third kind of way to represent color and temperature, is something known as the color index. And the useful feature of B minus V is all you need is a filter and a camera, and you can at least get an estimate for the color of the temperature of a star by subtracting its B minus V. So that's kind of a a little cheat that you can do. Okay, that's not bad.